Okay. All right. Hello, everyone. Welcome to the lecture number 1 of our course on numerical analysis of electrical devices. Today, we have the theoretical session about introduction to the theory and electromagnetism. And we also start talking about electrostatics and some information about capacitors that will be useful for your next lab work. Right. Every time I will put the title, date, and some particularly useful chapters from Height and Bach book on engineering electromagnetics. So if you need more information, please read these chapters from this nice book. All right. So let us start with the discussion about the vectors and their importance. Okay, so vector. What is a vector? Vector is an object that has a magnitude and direction. Right. This is the geometrical meaning of a vector: magnitude and direction. There are many examples of vectors: velocity, acceleration, electric and magnetic field, and so on. Usually we denote vectors by these boldface letters like this, or with a little arrow on top the letter. We probably will use both ways. Important point about a vector is that it is physically existing object. Okay, so like a velocity or electric field. It is something that exists regardless of the coordinate system we use to describe the vector. Okay, let us talk, for example, about velocity, like shown here. If I introduce a particular coordinate system, usually it is this Cartesian rectangular coordinate system invented by Descartes some time ago. I can represent my vector by projecting it on the all three coordinate axes, x, y, and z, with the corresponding unit vectors, ax, ay, and z. Right. So this way, when I project my vector, I get a column with 3 components, vx, y, vz. It's important to understand that if I change my coordinate system, rotate it, all components will change, of course, right? For example, for a particular vector of velocity, I can rotate my coordinate system to align velocity with the x direction, for example. Then I will get on the vx, and then vy and vz will be 0. However, this rotation doesn't change the velocity itself, right? Because velocity is something that truly exists. This is, for example, the velocity of my vehicle moving. Of course, the change of the coordinate system doesn't change that. For this reason, we call about so-called covariance of a vector. So vector is a covariant object, meaning that the components of the vector change upon changing of the coordinate system, but in a very specific way that leaves unchanged some characteristics of the vector. And here we're talking about mainly magnitude. So the rotation of this coordinate system doesn't change the magnitude of the vector, which is the length of my arrow, right? Yeah, here as an example, I bring this second Newton's law, F equals ma, right? F is the force, m is the mass, a is the acceleration. In this physical representation in the vector form, it is fair regardless of any coordinate system. However, if I introduce my coordinate system, particular one, x, y, z, I've got components which are which change upon the change of the coordinate system. So you can say that this vector form is a physical form. It is well, something that is objective, but the component form is subjective. It's not well, these components are not real. These are just mathematical abstractions. Okay, so in order to describe a physical system, we introduce the coordinate system. As I said, a few notations here. So first of all, the plane, right? We introduced the three-dimensional coordinate system. We've got three planes. One which is orthogonal to the axis x. It is called x0 plane or zy plane, and so on for the other two. The origin, and so on. So having the coordinate system introduced, we can assign the coordinates to any point in our space. Here, for example, the point P and Q with particular coordinates. Again, if I change my coordinate system, these coordinates will change, but this change doesn't change the point itself. Right. This allows us to calculate, to find the distance between the 2 points. And you notice that this distance is written in a way as a difference between x, y, and z coordinates. This is exactly what enables this covariance, because the way as you change the coordinate system, x2 change, xy change, but they change in the same way. So the difference doesn't change, leaving this d, this distance, covariant. Another way to describe any point in our space is to assign the radius vector r, right? And doing this, for example, for these points P and Q, right, we write this radius vector to the point P, to the point Q, and we can find the vector that connects these points P and Q, right? It's just the difference, difference between the two radius vectors. Yeah, so this way we can describe any vector in our space, even those that don't start from the origin, any vector, as the difference between the two radius vectors of the beginning and the end of this vector. Similar way, since our vector is defined by 2 points, right, origin and end, we can calculate the magnitude of the vector, and normalizing a vector by its magnitude, we can introduce the unit vector, which points in the direction of this vector b, but having the length of 1 unit. Once again, during my talk, please interrupt me at any point if you got any questions. But this is, of course, very simple and straightforward. I'm just trying to put us on the same page, right? Speaking about vectors, we introduce we can do, of course, we can sum vectors, we can subtract vectors, and so on. Particularly important to refresh our knowledge about the dot product and cross product, right? The dot product, by default, it's a multiplication of the absolute values of the vectors times cosine between directions of vector A and B. So if these vectors are orthogonal, the dot product is 0. When the vectors are collinear, then it's going to be just the product of the absolute values. For example, a particularly important point formulas that you should kind of remember is this in the red box. So when you multiply the unit vectors I by I, j by j, k by k, you get 1 because the length, the magnitude of these vectors is 1. But when you dot product different vectors, you get 0 because the vectors are orthogonal. There is a very important formula to remember about the dot product of two vectors A and B, which is given by the sum of the product of the corresponding components, right? And how we obtain this formula? So by definition, the product of vectors A and B can be represented by these two. I mean, writing the vectors by components, we can rewrite them this way. And then expanding the parentheses, right, we get this expression that continues for other terms. And we see from this red box formulas that the most of the terms go vanish, right? So we've got, for example, for this part, we've got this ax bx, and I times I gives us 1. So this is the first term in this formula, and the same way you get the other two. And of course, the vector dot the same vector is basically the magnitude of this vector squared. Pretty simple. Cross product, right? Cross product is something more sophisticated. When you do cross product, you got another vector, in contrast to dot product, which generates a scalar. Cross product generates another vector from two vectors, right? So by definition, a cross product is the product of the absolute values times sign between the vectors, and the direction of new vector is orthogonal to both, to the vector A and B, or orthogonal to the plane in which vector A and B located. Okay, and the direction also is defined by the this screw rule, or by this right hand approach rule. Following this definition,
Professor, I have a question. What does the lowercase a with the n mean?
Yes, this is the unit vector in the direction of the new vector, right? So doing A cross B, we got a new vector.
Yes.
And this part here, A, B sign, corresponds to the magnitude of this vector. AN gives you the direction of this new vector.
Okay. All right.
Right. And this AN basically points down to, I mean, is collinear with vector A and B. So following this rule, this definition, we find that for the unit vectors I, j, k, the cross product of I times I, j times j, k times k gives us 0, because the sign of theta is 0, right? But the other products, like I cross j gives you k, and so on, with the cyclic replacement of the vectors. Like if you do the clockwise cycling, this k goes to the place of j, j goes to I, and I goes to k, you get the second one, and so on. Yeah, so this is basically because these I, j, k are orthogonal vectors. Again, writing the result, this vector c, as the product of A vector and B vector, and expanding the parenthesis, we got the expression like this with more terms, of course, going next. But some of these terms equal to 0 because of this rule above, and the others generate the other vector, like I times j generates k, and so on. And if you write down the result, this is the result. So this is the component cx of the new vector. This is cy, and this is cz of the new vector. And remarkably, you can rewrite this formula using the definition of this operator. Yeah. So, any questions regarding this? People still coming. Okay. We need to recall some information about the vector operators. Okay. So when we introduce the vector operators, we start from the nabla operator. So this nabla operator is denoted by this nabla, right? And then this operator consists of 3 components, each one multiplied by the corresponding unit vector. So let us, for example, look at this I times d over dx. So d over dx, this curly d over curly dx, means the partial derivative, right? So I took my derivative with respect to x, considering other variables y and z constant. Okay. Then for the second term, I do my derivative by y, considering x and z constant, and so on. Written in this way, it is just operator. So operator, it means that it acts on some function. Okay. Functions can be scalar and vector. Let us look at the scalar function first. So if you consider a scalar function f, so you see it's not bolded letter, so it's a scalar, like temperature or pressure, or in electromagnetism, it can be the scalar potential. We can act this nabla operator on this scalar field f, and this is the result, right? This is something that we call a gradient, and the physical meaning of a gradient is that it describes the slope of a scalar field. Our scalar field changes in space as a function of x, y, and z, and the gradient indicates the direction of the fastest change of our field. As I said, the function can be vector, let us consider vector A bolded letter. So this is a vector. Nabla operator is a vector operator. And now it acts on a vector field A. So this product, this action of Nabla operator and the vector field can be dot or cross, right? Let us consider dot first, the dot product. Similarly, like we did here in this formula here, we can write the components for the Nabla operator, components of the vector, and then expand the parentheses. We will come to this formula here. So it's just the sum of partial derivatives of the corresponding components, dAx over dx, day over dy, plus dz over dz. So the result is a scalar, is a scalar field. So the divergence is a way we generate a scalar field from vector field. The importance of divergence is very important. It describes the source and sink of our vector field. For example, wait, yeah. Does it work? The animation? No, it doesn't. Anyways, yeah. So here I try to put this picture of a field with a positive source and negative source. So you can see that this positive source generates some arrows, right? The field that starts from this positive source and points outwards. The green source is the sink, so it's negative source. The arrows goes inside, inward of this source, so it's a sink, right? And if I calculate divergence of this field around the positive source, I will get the positive value, and the value itself will generate, will correspond to the power of the source. Okay, so some source can generate just a few lines of vector field. Other sources can generate a lot of lines of the vector field. So the magnitude, the value describes the power, and the sign describes the either source or sink. Finally, the last operation we need is called curl. Okay, so it is a cross product of Nabla with vector A, vector field A. Again, doing the same operations, representing the Nabla and vector in parentheses, then expanding parentheses will result in this expression here. The meaning of this new vector field is that it describes the rotation in my vector field, yeah, like this. So here I represent some curl field, right, around the origin. So if I calculate the curl of this field, I will get some non-vanishing, non-zero vector field, the field of the curl. Yes, so three vector operations, the gradient, divergence, and curl. Please remember them, and remember also the physical meaning. Okay. We also need two integral theorems, which are very easy to remember. The first integral theorem, or so-called Gauss theorem, dictates that the flux of vector field A, vector field F, through some closed surface dV. Okay, so here as an example, I draw this rectangle, right, like a cube, and this surface integral runs over the surface areas of each face of this shape. F times dA corresponds to the element of flux through this surface. So the flux corresponds to basically to the flow of some vector field through some area, right? Like you can imagine some sort of a flow of water through some area. This is the same meaning. So flux of some vector F over the closed surface. So this circle here indicates closed surface. Is equal to the volume integral over the volume of this body encapsulated, I mean, enclosed within this surface. And the integral includes this divergence of this vector field. Okay, so physical meaning is very simple. Since in vector field, some vectors go in this volume, some go out from this volume. If the volume doesn't contain any source, recall divergence describes the source and their power, right? So if no source, then the number of vector lines that go in equals to the number of vector lines that go out, no source. However, if this volume embraces a source or some number of sources, then this integral on the right won't be zero, and in result you get some not vanishing net field flux through the surface of this body. So this theorem allows you to to write three-dimensional, like volume integral through the surface integral. There is another theorem called Stokes theorem, right? It allows to do something similar, but downgrading surface integral to the line integral. Okay, so here on the left, we have the line integral over closed line that encircles some shape. In this case, it is open shape, not closed. Okay, and this theorem allows to find the flux of the curl. So recall this nabla cross F is a curl F, right? So it is the last vector operation that describes the vertices in my vector field. And since it is a vector itself, the curl, I can find the flux of this curl vector through some area A or sigma in this picture. And this theorem allows to calculate this flux by integrating the field itself, F, over the closed path that describes the edge of the surface, right? Not only edge, but in any across any closed path that belongs to this surface gamma or sigma. So the importance of these theorems will be clearly seen from the following. So finally, we can say a few words about Maxwell equations. So Maxwell equations, I mean, of course, you familiar about Maxwell equations, or at least supposed to be, because Maxwell equations are in the heart, in the center of the electrical engineering. So Maxwell equations, they describe basically everything around you, any technology, cell phones, internet, computers, electricity, everything, with some with a few examples. Okay, let me say this way. So like quantum, they don't describe quantum. Like light emission, they don't describe light emission. But the rest is described by Maxwell equations. That's why these equations are so important, and we need to discuss them. Also, our course about numerical simulations, and numerical simulations of what? Of Maxwell equations for different systems and different scenarios. All right, so the first Maxwell equation is so-called Gauss law for electricity. So you see this divergence of electric field is equal to some function, a rho over sigma 0, right? So here rho corresponds to the charge density. It is a function that describes the charge and charge distribution in space. Okay, and epsilon 0 is just a constant, is a vacuum dielectric permittivity with some particular value. So it's just a constant, right? So important meaning of this equation is that the divergence of electric field is given by the charge density of our system, of our charge distribution. Okay, so it's in line with the physical meaning of divergence. Divergence gives us the power of the vector field, right? Which is the charge. So it is very easy to grasp. Just like the second Maxwell equation, which is Gauss law for the magnetism. In drastic contrast to electric field, for the magnetic field B, this right part is equal to 0, indicating that there are no magnetic charges in nature, in the world. There are some alternative physical theories that predict the existence of magnetic charges, so-called monopoles, and the consequences that we would have from existence of these magnetic charges. However, they all don't work, and researchers didn't detect any magnetic monopole so far. So we assume that the divergence of magnetic field is equal to 0. So no charges of magnetic field. At the same time, it means that for any system, for any conditions, magnetic field must be always closed. Like the vector lines for the magnetic field must be closed lines. They cannot start and end at any point in nature. So the third Maxwell equation is called Faraday's law of induction. This is one of the most important. I mean, all these equations are very important, but this is very important to grasp, and very easy to grasp, by the way, because it just connects the time derivative of magnetic field on the right side and the curl of electric field on the left side. So the physical meaning is crisp clear, right? The change of magnetic field in time, any change of any magnetic field in time, generates the curl of electric field. If you have magnetic field and it changes in time, it creates the curl of electric field.
Sorry, excuse me. The curl of electric field. Sorry, could you explain it again, like what it is?
Curl means it is it has the shape like this. It gets a vortex. Curl means it rotates around some point, something like this. So let's say I have for example, have magnetic field that points in my monitor, right, in this picture, and this magnetic field changes. So this change of magnetic field creates this circle of electric field.
Yep,
right?
Thank you. Yeah.
Yeah. Just give you one example of our recent, I mean, when this became so important. So we recently very interested about the physics of MRI, you know, this magnetoresonant tomography. Doctors used to, for example, detect the illnesses like cancer and so on. So it's very popular technique today. And surprisingly, I mean, not surprisingly, but this MRI system, it uses the strong magnetic field which changes in time. And this change in time of magnetic field, of course, generates the curl of electric field. And this curl of electric field sometimes becomes harmful in some particular cases. Okay, so in general, MRI is very safe, but this factor of fast changing of magnetic field generates electric field, which can be harmful, especially in high field MRI systems. And you can name other systems where the change of magnetic field creating electric field can be harmful. Okay, like people today develop wireless power transfer to charge electric cars, right? Like inductively. They use this magnetic, the coils coupled through magnetic field, and this magnetic field changes in time, and it generates electric field, curl of electric field, which causes some eddy currents. We're going to talk about this next, I mean, in another theoretical session, but this is important to recognize. When magnetic field changes, it creates electric field. Similarly, to the last Maxwell equation, Ampere's law. Here, similarly, we have on the right side, we have the change of electric field and the curl of magnetic field on the left side. So change of electric field in time creates the curl of magnetic field. Also, it includes the current term, which dictates that not only electric field and its change in time, but also the current itself can generate the curl of magnetic field. Right. So let us look at this the Faraday law, for example. Let's suppose I have magnetic field that changes abruptly in some area of space, right? So it changes in time. This change in time of magnetic field unavoidably generates the curl of changing in time of electric field. Then I go to this Ampere's law. Changing in time of electric field generates the curl of changing in time magnetic field, and so on. So it works like this. This is a system of equations, meaning that you cannot solve, for example, this one without solving the others. You have to solve them all together. They are connected. In general, they are connected. And this is the origin. This is the reason why electric and magnetic fields can propagate in space without any charges in form of electromagnetic waves. So if you change electric field, it creates magnetic creates electric, and so on. So wave can propagate without any charges. This is something we will discuss more in what follows. But now let us consider a particular case of electromagnetic fields when electric field doesn't change in time and magnetic field vanishes. No magnetic field and electric field doesn't change in time. An example could be just the field of stationary charge, right? So let us see how we can derive the equations of the electrostatics. So this is the case of electrostatic, no change in time of electric field. So the first Maxwell equation stays unchanged, except for the fact that the electric field here is not the function of time, but can be function of in space, which is indicated by this equation. So next, the Faraday law leads to the fact that the curl of electric field vanishes because here, without magnetic field, right, this equation, this curl of electric field vanishes, equal to 0. So this is my second equation. The fact that the curl of electric field is 0 means that my electric field has no rotations. Okay, so it is it points like for example, outward or inward to a charge. So no rotations. So it is rotationless field. Such rotationless field can be formally presented as a gradient field of some scalar potential. So here we introduce this concept of scalar field. Once again, if we have no curl of electric field, this allows us to write this electric field as a gradient of a scalar field. Indeed, if you substitute this gradient of scalar field to this Faraday law in this case, the curl, since the curl of gradient is always zero, this is another theorem. Curl of any gradient field is always zero because gradient is rotationless field. And this satisfied, I mean, 0 equals to 0. So we can represent electric field as a gradient of scalar field, which is important because solving the equation like this for the electric field requires solving it for each component of electric field, which means that instead of one equation here, we have actually 3 equations for each component of electric field. However, solving the problem for just one scalar field is obviously much simpler. That's why this concept of scalar field is so popular. And in fact, the problem that we're going to solve today utilizes the potential, the concept of potential. So now let us substitute this gradient of scalar field to the Gauss law here. This is the result, right? Dividing both parts by -1 and taking into account that nabla times nabla is nabla squared, it's Laplacian, it's just another operator. You simply take the nabla operator from this function twice. You come to the final result, the Poissonian equation. So the Poisson equation, which connects the potential, scalar potential, and the distribution of electric charge in the space. Now let us derive probably the most important formula for electrostatics, right? So-called Coulomb's formula, Coulomb's law. Let us start from this Gauss theorem, right? The divergence of electric field is equal to the charge density. And represent each charge as a power of this charge, the charge value, Q, right? Like for the electron, it is the charge of the electron. For the proton, it's the charge of the proton, and so on, multiplied by delta function. So delta function is simply a function which is equal to 0 everywhere except for the location of the charge, where it's equal to infinity. Okay, so since Maxwell theory is a microscopic theory, we don't describe the electron itself, or what parts like it consists of, what is the actual distribution of the charge inside the electron, and so on. We just describe electron or proton, whatever, by a point. Okay, and for the point, we cannot say that the charge has some distribution. The best we can do is to say that the charge is all located in this point. So we multiply this charge by the delta function, which leads to the correct results for the electron, for the charge density. So this is the result. I plug in this rho function to the Gauss formula. Let us consider this for a single charge Q surrounded by a enclosed spherical surface A with the element of surface dA, right? So this charge creates the electric field E. For the positive charge, this electric field will be going out from the sphere. And the R gives us the radius of this auxiliary sphere, right? So this is just mathematical abstraction, auxiliary sphere, that allows us to integrate the Gauss formula, this one, by volume, right? So you take the volume integral from this Gauss formula. So the part on the right gives us the integral of a volume from the charge multiplied by delta function, which is equal to just the charge. So this is the result. The charge enclosed inside of this spherical area. The part on the left, the integral of the divergence of electric field can be rewritten as a integral over the surface using the integral divergence theorem or the Gauss theorem. This one. I use the fact that the volume integral of my divergence of the field is equal to the surface integral of this field over the surface. Yeah. So this is the result. So now let us use the fact that if the charge is sitting in the center, right, the system gets the spherical symmetry, and of course, electric field is not changing. It is not a function of orientation of the angles theta and phi. So the electric field on the surface of this auxiliary sphere is exactly the same. This is illustrated by writing the electric field this way. So it is a function of distance, but not the orientation in space. This allows us to take this integral here over the surface. So plug in this formula to the surface integral. And recognizing the fact that the electric field is the same at any point at the surface, right? So I'm integrating over the surface. So I don't care about the points inside this volume. I've got this. I can take this electric field out from the surface integral, and the surface integral of the sphere gives me the area of the sphere, 4 pi r squared. That's it. So I'm coming to the final result, saying that the electric field at a particular distance r from a point charge q is equal to the charge q over 4 pi epsilon naught r squared. So electric field decays as a function of r to the power of 2 from the charge. The electric field decays quadratically as a distance from the charge. At this point, we introduce the concept of the force, because in fact, how we detect the field and the strength of the field by using another charge, which is called probe charge, that we introduce inside the field created by another charge, and measuring the force. The first one is causing on the second one, right? So for the force between the charges, I need to multiply this electric field by my probe charge, and we coming to the final Coulomb's law, Coulomb's formula that describes the force between the two charges. The formula is symmetric according to the charge Q1 or Q2, which means that this force is exactly the same. The force one charge acts on the second one is exactly the same as the second one acts on the first one.
Professor.
Yes.
This is just describing how capacitors work in a nutshell, right? The strength of an electric field that a capacitor has with the distance between the two plates, between the dielectric constant.
Yeah, I'm coming to that.
Okay.
So probably next slide will be about capacitor. Yeah, this is the illustration of the interaction of the charges. Yeah, before talking about capacitors, let us talk about dielectrics and metals and conductors in electric field. Starting from dielectrics. So what's happening when we apply electric field to a dielectric? Why it's not? Okay. So when we take a piece of dielectric, which is described by the fact that it has no free charges, right? The dielectrics cannot conduct electricity, which means that they have no free charges. All charges are bound, like electrons bound to the nuclei, and so on. So the best they can do only deform. The atoms can deform, and this deformation leads to polarization of the material. Right? So when we apply electric field to the piece of dielectric, it gets polarization. This polarization state is described by a new vector, P capital, called polarization. And since this polarization is proportional to the value of electric field, we introduce a new coefficient, this coefficient of proportionality. It's called susceptibility, or sometimes we call this polarizability. So basically this function kappa describes the power, the strength of the polarization. Some materials polarize weaker than other materials. For example, we have some specific. No, actually, more important example is water. Since water gets big molecules and they are deformed, you know, hydrogen, 2 oxygen. So 2 atoms of hydrogen, 1 of oxygen. The shape of this molecule is like triangle. So it gets a strong dipole moment. And if you place water inside of, if you apply electric field to water, the water gets strongly polarized because their molecules rotate along the electric field. And this fact leads to some important consequences that we also will discuss later. So polarization, and we describe this polarization by polarization function P and polarizability. Since we got polarization, we need a new letter for the field inside of a dielectric. We call this letter D. So this is a D field or displacement field. And mathematically, it's just the sum of 2 electric fields plus polarization field. Okay, this electric field is the field within dielectric if no dielectric would be there, like the field we apply, the bias field. And P is the new field that is generated inside of the dielectric because of the polarization. And the sum of the two is our resulting field, the displacement field D. Substituting the formula for P through susceptibility to this one allows us to write the displacement field as a linear function of electric field, introducing the dielectric permittivity function, epsilon, which is equal to epsilon 0 times 1 plus susceptibility. This is another formula that should be memorized, but we're gonna discuss this later much more. Finally, of course, if the electric field is too strong, it can cause some destruction of the material, of the electric, with formation of plasma, which is essentially the appearance of the breakdown neutral atoms and formation of positive and negative charges that are free to move. So the electric can get this dielectric breakdown effect. One example is, of course, the lightning, right? Lightning is just the breakdown of atmosphere upon very strong electric bias between the ground, the earth and clouds. So conductors in electrostatics. Conductors in electrostatics is much simpler, because what essentially happening here? So let me take a piece of conductor, like a spherical particle, and place inside of electric field. This electric field, of course, causes the negative charges and positive charges, right, on the opposite areas of this body. And since there are so many electric charges in conductors, the field that generates this that is induced by this positive and positive net charge and negative net charge, right? These charges now create the field that points in the opposite way to the applied field. And the other two cancel out. So you come to the fact that in electrostatic, the electric field inside of any good conductor is zero. It vanishes, because any external electric field will be immediately cancelled out by the induced internal electric field from these induced charges. Okay. Another example of metals, of conductors in electrostatic, if you take one charge and surround this charge by a metallic shell, this positive charge, for example, will create the induced negative charges here. And these negative charges, of course, they are some extra amount of electrons, right? And these extra electrons came from other areas of this object, from the opposite surface. So this opposite surface gets the positive charge, and this positive charge creates the field that reminds the field of this positive charge as if no metallic shell would be around this charge. Okay, so if you look at this system from the distance, so this entire system will be very small. The field of the system, you wouldn't tell if this field from this complicated system or just the field from the point charge. So it will remind the field of the point charge. And finally, if you take a metallic or conducting object like sphere like this and charge it, for example, by positive charge, all these facts lead to the fact that the electric field inside of this object will be zero because of the screening effect, and will depend on the distance as if this sphere would be just a point charge, right? So this is the Coulomb's law, essentially. At the same time, the potential inside of the metallic object will be just constant, okay? Because what is potential? Essentially, potential is the energy that you spend to bring a charge from infinity, let's say, to the system. And the change of the potential is essentially the voltage, right? This is the reason, this is what causes the current in a system. So if the potential would be different inside of metallic object, it would immediately cause some currents that would lead to dissipation of the current, and eventually the system will come to the constant distribution of the potential inside of metallic object. And the outside, again, it reminds the potential of the point-like charge. We will do very quick simulation today to confirm that. So finally, capacitors, just a few words, because we're gonna discuss more about capacitors in our simulations next week. Right, so capacitor essentially is a device that can store charge and store electric field energy. So let's say I use some battery and take some negative charges, which are electrons, and move them to the other plate, right? I consider the system of two metallic plates. Metals are very good conductors. So I can take some electrons and move them from upper plate to the lower plate, which will charge the upper plate with positive and lower with negative charge. In this case, this situation of positive plus and minus, it will stationary, because as you know, the positive and negative charges, they attract each other, right? So this configuration can be stable. If you remove your battery, the charge will be there, the field will be there, because positive and negative charges attract themselves. So when describing the capacitor, we need to introduce the concept of voltage, which is the difference between the scalar potentials, phi1 minus phi2, right? This charge of the capacitor leads to the internal field, which is given by the voltage or the potential difference between the plates, divided by the distance between the plates, Again, we will discuss much more next week. And the way we describe the ability of a capacitor to store the charge and the electric field is by introducing the concept of capacitance. So capacitance is a quality that, or the value that describes the ability of a capacitor to store the charge. The larger capacitance, the more charges we can deliver, we can store within the capacitor. Today, we have this, for example, we have these supercapacitors. I forgot the name. But I mean, supercapacitors is another name. So we use even we use them even as a battery, right? Like whenever you charge your stylus, for example, you charge a little capacitor that is sitting inside of your stylus for writing, for example, on a tablet. So this capacitor provides can work as a electric source of electricity. All right. Yeah, the final one, the superposition principle. Very quick. Superposition principle means that the field from a system of charges simply equals to the algebraic summation of all fields from all charges, right? And why it's important? It's important because instead of calculating the electric field from a complex object, you can discretize this object by small pieces, calculate electric field from each piece, and then sum up all these contributions. Essentially, this is the approach we use for numerical simulations. By doing so, we introduce the concept of charge density, which we already used, but essentially charge density is the ratio of the charge within some volume divided by the value of this volume, right? And then you take the limitation of this volume to 0. And in this case, doing so, you can convert the summation of the charges to the integral of the over the volume using the charge density function. So this brings us to the last point of my today's talk about ANSYS Maxwell 3D. So ANSYS is the name of the solver we will learn. How it works? It uses the finite element method, in short, FEM. FEM. This approach is pretty much straightforward, right? For example, you have some object, you can discretize this object, including the area within the object, by this unit elements called mesh cells. These mesh cells can be of different shape. For example, for this tetrahedral mesh type, we got these tetrahedral elements which form this like a mesh or net that discretizes our system. And then we solve the problem for each element and then sum up all the contributions from these elements, right? This is a very bulky problem, but for a computer, it is very straightforward. You just compute the fields contributions from each element. Of course, the finer discretization, the larger number of mesh cells, so the computation volume is greater, but this problem can be solved by computer. The problems we're gonna solve in this course, we can use just simple desktop computer. Using more powerful computer, you can simulate electromagnetic fields scattered on a plane, for example, or something like that. So much more sophisticated problems. I saw pictures of scatterings of electromagnetic waves on a warship. Okay, so it's the larger problem, the more powerful computer you need, but in general, it is just the matter of computational powerfulness, how much complex problem you can solve this using this approach. So, for example, let us look at this system once again. The conducting sphere charged by positive charge creates the electric field distribution like this. This is something that we know from analytics, right? Doing numerics, what we do, we discretize this sphere using this mesh cells approach. Then, in each mesh cell, we solve the Poisson's equation that we discussed today, right? For the distribution of the voltage or the scalar potential V, and then for the calculated V for the potential, we can calculate electric field distribution by taking the gradient of this field V. Very good. So next week we will do the first lab work simulating a parallel plate capacitor using the ANSYS Maxwell 3D simulator. And today, let me quickly show you how it works, like a quick introduction to the ANSYS simulator. Okay, so this is the ANSYS electronic desktop. This is the window you see when you run the program. It includes several solvers, and the one we will use is this Maxwell 3D design solver. So you run Maxwell 3D. So it creates the numerical problem space. So what you do next, you create the sphere, right? We're simulating the sphere. Let us make this sphere made of very good metal. We call this perfect electric conductor. So I search for the PEC, perfect electric conductor. Then what I can change the color, for example. Apply OK. Then I need to change my the size of my sphere. I can parameterize this, for example, assigning the R is not allowed sphere, for example, like this. Let's make it 10 millimeters, for example, located in the center. So this is my sphere with the size of 10 millimeters. Then I need to define the area around my object. So let me do something like 50 millimeters sphere area around. So whatever inside this area will be simulated, right? So then what I do next, I charge my sphere. Okay, so I highlight my sphere, and then oops, I can remove this by view and hide selection. Yeah, so now I charge this sphere by assigning excitation I forgot to change the solver. So Maxwell 3D solver type, electrostatic. Yeah, this is something I always forgot about. And we can save it. So now I can change, I can assign the excitation as a floating charge. The floating charge, for example, one nano coulomb, right? So I created the charge over the sphere. Next, what I need to do is to say where is my potential zero. So I require that the potential over this region, right, is zero, which mimics the open boundary conditions. So I create the excitation over the surface as a voltage and required to be zero. What next? I create analysis. I need to create analysis, which basically indicates how precisely I calculate my system. And what else? Then I need to validate the problem. So it's check marks all green. So my problem is ready to be executed. And I believe, yeah, I can simply run it. So I just run the simulation. During this simulation, I can go to solution data to check how my project converts. Let me see. If this terminated, may have run out of memory, could have been killed by user. No. Let me run it again. What's the problem? Give me a second. It should be fine. Interesting. I didn't expect it to run into any problems. Space. Maybe I ran out of space on my hard disk. Okay. Let me save it maybe to another place. Interesting. Maybe some problem. Still. This is weird. So now it's running. Interesting, what was the problem? So here we can we can check how the problem converges, plotting energy error. Solving is done, but I don't really like it. So let me see what we got. So when the problem is solved, I can see quickly the field distribution. Field. No, this is something totally wrong. What's wrong with my model? I can I can open the project that I did just today, because I'm not sure what was the what is the problem. So this is the project I tested today. It is exactly the same project. No, not sure what what happened. So the idea was to oh my god. No, this is another one. This one. this one. Yeah, so the idea was to show you that this charged sphere. So here I plot the electric field distribution, which is this plane with 0 inside. The blue means 0, right? So this is 0 field inside. The field in the another plane indicates constant potential inside of the sphere. So this is the potential. And more interestingly, you can draw a line. Here I draw this line and plot the field along this line. For example, for the magnitude of electric field, the simulation gives you this. So 0 inside the sphere, then abrupt jump to some high value, right? And then this 1 over square root of 2, or sorry, 1 over r to squared dependence of the electric field as you go further from the particle. I also wrote a simple, in Python, I plot the same result, but using the analytical solution, right? So this analytical solution allows me to plot the electric field from the radius of the particle, right? And this is the result. So the analytical solution gives you this value at the surface of the particle, like almost 90 thousandths of volts for the given charge. And the numerical solution also gives you 90 thousandths of volts at the surface of the particle. I'm not sure what happened to this project. Maybe I ran out of space. It says something like, yeah, the execution error on server. So something wrong to the server. So it's the problem is not on my side. It's the problem of on the server. So I just hope that it will be resolved by our next meeting, right? And you will have no problem with running the simulations. All right. So you see the principle, the approach we use to numerically simulate this particular problem, and it works exactly the same way for more complicated systems. All right, so do you have any questions about this part? Let me stop my recording.